All right. Hello, everybody. Thank you for coming to this workshop. Today is April 8th, 2022, and I'll be talking about parallel computing in R for the Statistics Club here at UTSA. And thank you so much for coming. So the first thing I want to talk about is introduce myself. Hello, my name is Victor Feagins, and I'm a statistics and data science major here at UTSA. I'm graduating this semester, and my next step is I'm an incoming PhD student at Wisconsin-Madison. So that's what I'll be in the fall, and wish me luck, and hopefully it goes well. And so I've used parallel computing, my experience with parallel computing for various works and internships, various tasks that I've had throughout the years. I'm like, oh, this would be better. I could use parallel computing on this and do a good job. And so that's kind of my experience. And I'll talk a little bit about that a little bit later once we talk about why we do parallel computing. So first, I want to talk about assumptions. What am I assuming about you guys? So I'm assuming that you guys have knowledge about coding, like concepts of coding. So like the idea that we can do things on a computer, that we can work with files and make things happen. We can get results. I'm assuming you have some beginner statistics. So I'm going to be using some vocabulary like plotting, reading in data, the concept of data, modeling. So I'm going to be using these vocabulary words. I'm going to assume that you know what those mean. So some beginner statistics. And you don't need to know R for this talk, but understanding some of the R syntax will help in when looking at some of the examples. But it's the presentation portion of this workshop is very, very intuitive driven. It's by no means supposed to be like you leave this talk and you're like, hey, I'm a parallel computing master now. I have some code and I can run with it. It's going to be teaching the intuition. That's going to be the most important thing for this talk. So let's talk about what is parallel computing by first talking about what it is not. So parallel computing, well, what's not parallel computing is sequential computing, right? So series, things that run kind of in a line. So imagine we have an office space where there is only one computer in the office that has R, only one computer in the R, and there are several coworkers, right? Let's see, Susan, Bob, Kyle, John, and they need to do various tasks for their supervisor. And so Susan wants to read in some data, Bob wants to process some data, Kyle makes plots, John does some linear model, all right? And so series, they do this one at a time, right? So they line up at the computer, they do their task, they leave, the next one goes on the computer, does their tasks, and leaves. So this is a series. And so the total time that this process takes, if each of one of these tasks took 5 seconds, is 20 seconds, okay? Now, what is something we can do to make this faster? Maybe we can give everybody a laptop. Hey, we have money. Let's get everybody a laptop and see if we can make our work faster. And so, hey, look, if they do all their tasks at the same time, we can take 5 seconds. Hey, 5 seconds. We turned a 20-second task into a 5-second task. But what is the problem with this situation? Does anybody know? This isn't rhetorical. I want to hear. What do you guys think is the problem with them doing everything at the same time? What do you guys think?
It might stress the system.
Maybe stress the system. Okay, maybe like there's some problems, but look at the particular tasks. Look at what they're doing. Is there dependency in their tasks? Do they need to come in a certain order, you think? All right, well, there is dependency. For example, reading in the data, it has to be the first thing you do, right? You can't make plots if there is no data. Or you need to process the data first before you can model. So this is a more realistic of maybe using multiple computers if we wanted to make this more efficient, right? Where we have the processing sector where we read in the data and then we process, and then we kind of give John and Kyle their own computer. So one of them does modeling and the other one does graphing, right? So this is more realistic, but it is not probable, because these are very small tasks. They don't take a long time. And so usually in these situations, we don't pursue parallelization because it's just easier. Hey, 20 seconds isn't a lot of time. let's just, do it in series, right? It's easier. We don't have to worry about setting it up, right? Maybe owning these two computers is like cost benefit analysis. Oh, maybe we don't need those two extra laptops. What we are really interested in is the ideal parallelizable problems, also known as embarrassingly parallel. So here's the same office space with Susan, Bob, John, and Kyle, and they're each modeling COVID spread in the various states, United States. So Susan's modeling Texas, Bob's modeling New York, Kyle's Alabama, John is California. And if I get Kyle and John mixed up, it's because they're brothers. Sometimes I forget. Bob is easy. He's an Afro, like Bob Ross. And so say we do something like this, where each of them is doing this modeling task of modeling COVID spread, and each takes 30 minutes. Each task takes 30 minutes. There's 4 tasks, total time 2 hours, right? So, well, they're waiting in line. They're just sitting in the office space in line doing their tasks, and their supervisor is like, "What are you guys waiting around for? You guys are gonna wait in line and do nothing for 2 hours? You just one at a time? Come on, speed it up, speed it up." So they decide to give everybody a laptop, right? So this is a situation where these tasks are independent, right? So say we make the assumption that the COVID spread in Texas is independent of the COVID spread in Alabama. And so we can try to make these kind of independent tasks. So this would work, right? We give everybody a laptop, there's no dependency, they each do the results. Now, the total time that this took was 40 minutes. All this, everything was done in 40 minutes. Before, each one task took 30 minutes. Where did those extra 10 minutes come from? Does anybody have any ideas? Imagine you're in office space. You have your coworkers, they're each doing their individual tasks. What happens after everybody's done with their work? What needs to happen? Come together, a meeting, a group meeting. How was everybody's models? How did everybody perform? There's this communication that needs to happen. Communication is very important. Communication is the big limitation in parallelization when pursuing parallelized problems. Communication, some people call it overhead. So this is the time cost of setting it up. Setting up, giving everybody laptops, giving everybody the data, collecting all the information from the various clusters. So here we have the supervisor, Susanna, and she has all the US COVID data and she gives them out. She has to divvy up the data to all the workers, and then the workers do their modeling, and then she needs to get all the models back. And so this takes time, communication. So it isn't perfect. It isn't perfect. Even if it was 100% efficient and each task took 30 minutes, we still have this communication, right? This overhead. So this is where these 10 minutes come from. Now, any questions so far before we move on? So this is the intuition. Everything so far has just been the intuition. Any questions? Any questions? Okay. All right, so now, why do we do this? Why do we do this? So I think in my experience, why I've ever pursued parallel computing is because through a task I need to get done. My boss asked me to do something. I need this job and it's just taking too long. This isn't efficient. I'm going to be sitting here all week processing these data. And that's where what introduced me to parallel computing is having this task, having this problem like, hey, this is taking forever. And so some of the projects I've done in parallel computing, the very first project I ever did was compressing large amounts of data. So I was working with some engineers and they had a physics simulation model and they were outputting various numbers that this physics model was generating. And it generated over 120,000 CSVs on a local computer, 120,000 CSVs for one simulation. And we had 6 simulations. So that's a lot of CSVs, a lot of little tiny files with a bunch of numbers in them. So my job was to take all that data, kind of mush it all together and compress it so that it's easier to work with. And so I used Python for this task and I used the message passing interface to get this done. And so I got it working. I used Parallel. I gave it to my boss. Here, I wrote this code. It should work on all the simulations, and it did. We got it done. We got all this 120,000 files down to one single HDF5 file, which is this compressed data format. It's very cool, very magical. very magical, like 300 gigabytes to like 3 gigabytes. Very cool. Very cool. I recommend looking into it. The next project I did that involved parallel processing was modeling time series satellite data. So I was working with a environmental science lab, and we were using R, and we had distributed computing clusters. So we had a bunch of worker computers that we can get access to and divvy up tasks. And so my job was to automate and model this daily time series model that would happen. So the satellite, there are 3 images to be collected every 5 minutes. So that's around, I think, 80 images a day, which was around like 32 gigabytes of data to process. And so each image, you have 3 different time series. So from 3 different images, you have this image time series, this image time series, this image time series. And so we had to kind of combine all those and combine all the information from the 3 images time series, which were the various different wavelengths that the satellites they were interested in. And we use parallel computing. We're like, oh, hey, look, we can process all our cloud data independently of our infrared data and of our, what was the other one? Radiance data. These are independent. We can do this in parallel. And we did. And I used computing clusters for that. I was at Boston University with their computing clusters. So these are some tasks that I did that were like, man, this is taking forever. Right? I can sit here for hours and hours waiting for this to run while I'm just, twiddling my thumbs, or I can speed this up and make it more efficient. So how do we do this? How do we do parallel computing? So nowadays, we have each one of modern computers usually have multiple cores on them. So CPUs today, they have multiple cores, and by default, R, Python even only ever uses 1 core, 1 CPU at a time, right? When you run a script, it's going to use 1 CPU. That's it by default, runs in series every single time. Now, the first multi-core processor was invented in 2001, and R was first developed in 1993. So missed the mark. So going forward, like for example, with languages like Julia and more modern languages, you kind of see this parallel computing mindset kind of baking in, right, when these languages are being developed. But when R was first developed, it wasn't a thing. But fortunately for us, fancy computer scientists, software engineers have developed the tools for us to do parallelization in R and Python and all sorts of things. And so today we'll be talking about the parallel package in R. So it's included with every R, base R, this package. And there's a lot of different ways to do parallelization. So today I'm just going to be talking about working on your single computer, working on just using the multiple cores on your computer. There's a lot of different ways. It can get very complicated and very complex on the more kind of advanced use cases. But today I'm just going to focus on the intuition and just use the resources that we have on hand, right? We all have a computer in front of us that has multiple cores. And if you're interested in learning a bit about more of the high performance computing area in R, this the CRAN, the R team has this kind of page dedicated to it that shows all the different tools and equipment. So the parallel package, which is what we'll be talking about today, supports parallel computation, right? We're going to do some things in parallel. And there's 2 things that the parallel package does. It does sockets and it does forking. So what you need to know is that sockets is when you kind of create a new worker, right? You kind of have a separate independent worker. So you go into R, you say, yeah, give me a worker, and it's going to create one. Boop, and he's a blank slate. And you got to tell him what to do. You got to give him the tools, you got to give him the data, and be like, okay, I want you to do this. Forking, on the other hand, is basically taking a copy of yourself. You're going to take a copy of yourself, and that already has whatever you had before, and it's able to do new things. Unfortunately, forking is not available in Windows. So all these computers in front of us are Windows computers. So if you try doing some forking, it's going to give you an error. Like, hey, I'm on Windows. This isn't a thing. And something we won't talk about, but I want to make note of, is random number generation. So usually, those of you who are more advanced in statistics maybe usually set a seed, right? You do set a seed in the beginning of a script, and then you do some randomization, right? So it makes it repeatable, right? Now, when it comes to parallelization, you don't want all your workers to have the same exact seed, right? Like each worker is going to begin with the set seed 1, 2, 3. So then each worker is going to have the same random numbers. So you don't want that. And so there's some advanced kind of seed generation things to consider when working in parallel. But we're not going to talk about that today, but something to keep in mind so you don't get yourself into trouble. All right. So now let's get into show some code, right? So R, this is where the R syntax comes in handy if you're familiar with it, but by no means is it necessary. See here, we load the library parallel package. We can run the function detect cores, and it tells us, at least when I made this presentation, that I have 8 cores. 8 cores on my computer I can use. And this is how I make workers in Windows in R, is I do make cluster 2. It's going to give me 2 workers to work with. And if you were using a Mac, or you can make a fork cluster, but don't work on Windows. So we won't be talking about those. And then eventually you can just shut down your workers with the stop cluster function. So with your workers, right? So this is sockets, right? So each worker is a blank slate. They're just like if you opened up your R session and it was just everything fresh. So you got to tell it what to do. You got to give it the tools, give it the data, give it the equipment that it needs to work with. So here the cluster eval q function runs code as is from your workers. So here I'm going to give it my clusters. I'm going to tell it, hey, give me the tidyverse. I'm going to use the tidyverse. You can see here in my 2 clusters, they gave me output like, okay, hey, we got the tidyverse ready. We got these functions ready for us. I was like, great, great. Now we can use those in our clusters. So we can also send functions and variables to clusters. So here, let's make a variable A, and let's make a function square that just squares a number. And we do cluster export. So I already have the data and I already have my variables. I'm going to send them off to the workers. So, and then if I run cluster eval q, if I print, A and the square of A, look, I see in my 2 clusters, 2, which is A, and 4, which is the square of A. Great, message received. They got the info. Now, let's start talking about how we measure things. Since parallelization is all about saving time, so there's multiple ways of doing this, but the most basic way is just using the proc.time function, which just kind of gives you, it starts a timer on kind of how long things are taking. And so I'm going to run a for loop. This is a system sleep. So it basically tells the computer, hey, sleep for 3 seconds. Sleep for 3 seconds. And I'm going to run this 5 times, right? It's a for loop. It's going to iterate over sleep 3 times, right? So how long is this going to take? You imagine, well, it takes 15 seconds, right? You tell the computer to sleep 5 times, 3 times 5, 15. And this is running in series. So if we wanted to run this in parallel, so I start my timer and I do there's a par sapply function. So if you're not familiar with the apply functions, it's very good to become familiar. It's just a way to kind of avoid for loop notation. For loop notation is kind of slow in R. But basically what this apply function does is that it's going to run system sleep on a vector of 5 3s. So basically, right, it's going to run system sleep on 1 3 and another 3 and another 3. So 5 times again, right? 3 times 5 should be 15 if it ran in series. And you can see here, it took 9 seconds. So we saved time, right? We told the computer to sleep 3 times or sleep 5 times for 3 seconds. And because we had 2 workers working at those 3 seconds at the same time, it was faster, 9 seconds. And then now we're done with our clusters. We tell them to go to sleep, stop cluster. You don't want them running off in the background when you're not paying attention. So you tell them to stop. All right, so that is some of the basic intuition and some of the basic ideas. Any questions so far? All right, so let's go see an example. Let me see if I can get this going here. Let me open up my R Studio. Come on, R Studio, I believe in you. Okay, let's see here. Oh, okay. Now, let's see here. Boop, boop. Let's go look at my files. Let's look at my, shoot, it went too far. Give me a second here. Boop, boop, boop. I'm gonna stop sharing so I can readjust my screens here. when you have two screens and you can't look at one of them behind you, it's annoying. Extend, duplicate these displays, keep changes. Okay, awesome. So this is going to be easier now to do. Okay. All right, so let me get it going here. Let's see here. So I made up an example. So let's actually, you know what? I have some words on this example. So let's imagine that we work for the Department of Health, State Health Services, and our task is to map every county's risk levels using the Census Community Resilience Estimates. So the Community Resilience Estimates, you can read up all about them, but they basically kind of give you an estimate about the number of at-risk individuals. So at-risk being people who have pre-existing health conditions, maybe low poverty, just living in circumstances that kind of make them more at risk for disasters. For example, COVID. So if we're the Department of State Health, we kind of know, hey, where are all the people that are at risk? And so I'll show this again later, but the workshop folder is right there. So let's go and pull it up in R. So map example, mapping parallel in R. So you don't need to know the code. You don't need to understand the code. So, but I'm just going to go through the intuition here. So in R, you load all your packages. I'm going to read in the data. I'm going to process the data. I'm going to do, stuff like this. And eventually I'm going to make a map. So let's let that run. And it's going to run and just give me one working example. I always like, whenever I'm working in parallel, I like to have at least one working example. And then I try to work that example multiple times in series. And then I attempt to do it in parallel. That's usually my workflow. I get one working example. Then I run it in series, and then I run it in parallel, just to make sure everything is working well. And then let me make this bigger. Okay, but you can see here I made a map. The Bexar County, so this is where we are in San Antonio, and you can see the community risk factors are mostly downtown, very high downtown, right? You have poverty, more urban, pollution, right? It makes more sense for people to be at risk downtown. So now we want to do this for every county in Texas. Every single county in Texas, we want to make this map so that we can put all the maps together and send them to our boss. Hey, check out all these maps. So let us do that. So here, I make a function. So whenever you're doing stuff in parallel, it's really important to kind of write functions for things because it's going to be easier to work with because you don't have to write, copy, paste blocks of code. You just have a function that you can repeat multiple times. So I make a function. Why is this error? Okay. The function here is called Texas County Map, and it takes, hello, welcome. And it's going to take, basically going to functionize all this to make the map. And then I'm going to write a function that also saves the map. And then I'm going to run it in series. All right, let's hope this works. So what this is doing is using lapply, let's see if I can, view, zoom in. So right here, it's running in series. It's using lapply, which is just going to run over all the Texas counties, every single Texas county. It's going to run my save map function, which is going to make the map and save it for me. And it's going to do that in series. So this takes around a minute, I think. So we'll sit here. But eventually, we're going to do stuff in parallel. Right, so I call the parallel library, give me my parallel tools. I'm going to start doing some parallelization. And I start my timer. I'm going to make some workers. I'm just going to work with 3 workers. And I have to send them my data, Texas County Map, Texas GRE, right, my function and my data. Send them off to my workers because they are blank slates. They don't have anything. And then I'm going to run my library statements. So they know all the functions I'm going to be using. And this time I'm going to use a par lapply. So in series, I ran a lapply, and now in parallel, after doing the setup, I'm just going to run a par lapply. And we're going to see if it's faster or slower than series. All right, so you can see here, it ran in series, and it took 77 seconds. 77 seconds to run in series. So now let's run it in parallel and see how it goes now with 3 workers, right? And we can change it. We can make it up to 8, right? but we'll see how that works. So we're gonna run it. It's gonna make the workers. It's gonna give it all the data and the functions. It's gonna run all the packages, and then now you have a lot of packages. It takes a long time to boot them all up. But then see, I'm gonna run my par apply. You can see my 3 workers. They got the functions. They got the libraries. So running my par apply. We'll see how fast it took. So the first one took 77 seconds. It's probably a little bit slower than normal because I'm running Zoom and I got my presentation open and I got this mic and this and this and this. So it's probably running a little bit slower than normally would if I was only just doing R. And so now see how it goes. So here, we ran it in parallel and it took 40 seconds this time. So we were getting down from 70 seconds to 40 seconds. And we saved around 30 seconds. Pretty good. No cost out of me. I just used the extra cores on my computer. I just used the resources I already had more efficiently, right? I didn't have to buy a new laptop. I didn't have to set up a supercomputer. It was pretty easy. So I saved some time. So one thing to pay attention to is if you open your task manager and we look at your kind of performance, look at CPU generally, we're going to see it kind of jump up whenever we do parallel process. So let me see, I'll run the parallel again, just so that we can see kind of in our task manager, kind of like it working. So you can see here, CPU is at 22%, but once it starts doing that parallel apply, it's going to jump up. So let's see here. See, hope I'm right. Be embarrassed if I'm not. All right, so running that parallel apply. Let's see it. Didn't go up as much as I thought it would. It went to 32. If I give myself 8 workers, it's going to go up to 99%. At least on my practice, it did. Interesting. Well, something to keep in mind, to pay attention to your performance on the task manager. It's very handy, especially if you get too crazy, you might be exploding your computer. So don't do that. Don't explode your computer. All right, I'm just gonna wait for this to finish. But while that is finishing up, see here, it took 74 seconds. Interesting. That time in parallel. All right, let's go here. All right, so let's talk about wrap up. So what have we talked about so far? So I introduced the concepts of parallel computing. Right, the big ideas is that you have multiple workers and there's communication involved. Right, you send in the data, and ideally you want these tasks to be independent tasks. And so we saw an example in action. We saw my maps, and we can actually look at my folders here to see where it saved all the folders. So let's go find it. The map example, and you'll have access to all this code and things. See here in parallel, you can see here all the maps that's saved. So you can here's the Bear County map that we made. It's been saved. Awesome. I can ship that off to my boss. Now I have all the files and we zip them up, ship them off. All right. So we saw an example in action, like this mapping problem. And we just scratched the surface. So this was the very basics, very high level kind of intuition. That's what's really important, intuition, right? Getting the idea. And there's a lot of resources out there to learn. And it is a bit of a niche topic, at least especially in the R community. There's not like this one super resource that's like, read that one thing and you're gonna learn everything about it. When I learned parallel computing, I have had to watch like conference presentations, read documentation, read some blogs, and kind of pull in information together. And then, of course, in my own work, when you're testing it and experimenting with it, you learn it quite good. You'll be surprised at how fast you learn something when you work on it 8 hours a day. And so to learn more, so we talked about the parallel package. I really like the future package. So we didn't talk about that because that's just another step of kind of abstraction. And I want to just cover the intuition, but the future package is really nice. That's what I used when I did that project with the satellite images. I used future. as well as some more distributed computing methods, which don't usually involve kind of implementing parallel in a script, is having just a bunch of scripts. So if you need to contact me, Victor Feagins at my.utsa.edu is my student email. And if you're watching this like 20 years from now and I'm no longer a student at UTSA, which I will be not in a couple months because I'll be graduating, you can find me on LinkedIn, GitHub, and hopefully I'm working somewhere where you Google me and it tells you where I work. All right. So now that wraps up my presentation, the presentation portion of this talk. The next thing is the practical, which we'll be working on an assignment together. Well, I already know what to do. I already did it. But you guys will work on an assignment on implementing some parallelization on your own computer. And so to get these files is follow this tiny URL, and that's going to have all the exercise in it. And yeah, that's the practicum. Any questions on the presentation portion of this talk, this intuition? Any ideas, concern, confusion, perhaps? All right, well, awesome. Well, we're going to be people who are seeing this from the future. I'm not going to record the practical because there's probably going to be a lot of technical difficulties. So this is the end of the recording. And then we're going to work on some practical stuff. We're going to work on some dog images. Yeah, interesting things. All right, so thank you for coming for a talk. And if you, in the future, the Stats Club, follow us on our YouTube, Instagram, and in the future, going to do various events. But thank you all for coming. All right, awesome.